today's topic is resonance. So what is resonance actually? Actually, some molecules we cannot explain all its properties by using Lewis structure, because all the covalent molecules, their structure is explained by drawing their Lewis structures. For example, take an example like ozone. In ozone, there are 3 bond pairs and rest are lone pairs. So, ozone, it is represented like this. Or it can be represented like this. Right? Okay, ozone has only 3 bond pairs. So 3 bond pairs can be arranged as 2-1 or 1-2. 2-1 or 1-2. These are the 2 possibilities for ozone. Okay, and keep in mind the bond between 2 atoms is called bond order. What is bond order? Number of bonds between 2 atoms. That is called bond order. And more the number of bonds, lesser is length. Lesser is bond length. That means bond order is inversely proportional to bond length. So that means if we say these are Lewis structures of ozone, right? These are Lewis structures of ozone, and bond order is inversely proportional to bond length. More the number of bonds, lesser is the bond length. So let us take this as A bond length and this bond length as B. So it is a double bond, it is a single bond. So what is the relation between A and B? Either A is less than B, or A is greater than B, or A is equal to B according to this structure. So ये double bond है and this one is single bond. So more is the number of bonds, more is the bond order, and lesser is bond length. जैसे मैंने आपको एक और एग्जांपल दिया था कि कार्बन कार्बन सिंगल बॉन्ड, कार्बन कार्बन डबल बॉन्ड, कार्बन कार्बन ट्रिपल बॉन्ड. तो इसकी बॉन्ड लेंथ होती है 120 पिकोमीटर, इसकी राउंड अबाउट 130 पिकोमीटर, 134 या 133, और इसकी होती है सॉरी उल्टा हो गया, सिंगल बॉन्ड में 154 पिकोमीटर और ट्रिपल बॉन्ड की 120 पिकोमीटर. तो ये बॉन्ड का लेंथ का ऑर्डर है. सिंगल बॉन्ड मींस बॉन्ड ऑर्डर 1, बॉन्ड ऑर्डर 2, बॉन्ड ऑर्डर 3. तो बॉन्ड लेंथ का देखेंगे तो लेंथ सिंगल बॉन्ड की सबसे बड़ी होगी, डबल बॉन्ड की थोड़ी छोटी हो जाएगी, ट्रिपल बॉन्ड की और स्मॉल हो जाएगी. दैट मींस A is less than B. So now that means A should bond length A should be less than bond length B. but in actual, in real, both A is equal to B. So that means if bond lengths are equal, experimentally it is proved. What I said? Experimentally. Experimentally, when we calculate bond length, the bond length is one only, that is same bond length of these bonds. That means neither this structure 1 nor 2 is the actual structure of ozone. They are not the actual structure of ozone. That means ozone is not represented by any one of them, or we can say Lewis structures cannot explain all the properties of the molecule, or in other words we can say ozone cannot be represented by a Lewis structure, because if bond order is 3, so there should be either 2-1 or 1-2. There is no concept of fractional order in Lewis structure. So keep in mind that ozone has same bond order, and it is like this. Means both the bonds are more than single bond, less than double bond. They are more than single bond and less than double bond. Means they have fractional bond order. And to calculate bond order is equal to bonds between two atoms, 2 plus 1 divided by positions. That means its bond order is 1.5. It is neither 2 nor 1. It is 1.5. That's why. But this type of structure cannot be represented by Lewis structure. This is not a Lewis structure, and that is called resonance hybrid. This is the actual structure. Okay? And these are called resonating structures or canonical structures. Resonating structure or canonical structures. That means resonating structures or canonical structures are the one which are drawn for the molecule to explain its properties, but it cannot explain all the properties. ये जो structures हैं ओजोन के, ये एक्चुअल नहीं है, ये हमने ड्रॉ किए हैं to explain few of its properties, क्योंकि most of the properties matches. There are 3 atoms, there are total 3 bonds, 2, 1 or 1.5 plus 1.5. Okay, total 3 bonds are there, but ये actual structure नहीं है, क्योंकि experimentally it has been proved that OO bond जो हैं दोनों, उनका जो bond length है वो same है, but इन दोनों में से कोई भी ऐसा structure नहीं है जो explain कर दे कि bond order same क्यों है, क्योंकि ये तो हो रहा है कि एक सिंगल होगा एक डबल होगा, और सिंगल और डबल होगा तो बॉन्ड लेंथ शुड बी डिफरेंट, बट एक्सपेरिमेंटली बॉन्ड लेंथ इज सेम. इसलिए ऐसे स्ट्रक्चर्स को एक्सप्लेन करने के लिए जो नेक्स्ट कंसेप्ट आता है दैट इज कॉल्ड रेजोनेंस. डबल एंड सिंगल बॉन्ड दे आर नॉट द एक्चुअल स्ट्रक्चर्स ऑफ ओजोन. Actual structure is this one. That means resonance hybrid is the actual structure, and resonating structure or canonical structures are imaginary structures. They are imaginary structure of ozone. It is a phenomenon as a result of which a molecule can be expressed in different forms, none of which can explain all the properties of the molecules, the actual structure of the molecule is called resonance hybrid, and the Lewis structures drawn for the molecule to explain few of its properties are called resonating structures or canonical structures. Called resonating structures or canonical structures. Okay. Say, for example, that means it is the phenomenon as a result of which a molecule can be expressed in different Lewis forms. In different, we can write Lewis forms. Okay. None of which can explain all the properties of the molecule. For example, let us take example of benzene. Benzene is generally drawn like this: 3 double bonds, 3 single bonds, and position may be like these two. Okay, none of which can explain all the properties of the molecule. Okay, and the actual structure, these are the resonating structures of benzene. None of them is actual. Now look at these structures. In these two structures there is a carbon-carbon double bonds, 3 carbon-carbon double bonds, 3 carbon-carbon single bonds. Am I right? So there are 2 types of bond lengths. Say carbon-carbon single bond length is 154 picometer and carbon-carbon double bond length is 133 or 134 picometer. Okay, that means these molecules should have 2 types of carbon-carbon bond lengths, but in actual it is like this, a resonance hybrid. So all the experimentally it is proved that all the carbon-carbon bond lengths are equal, and that is equal to 139 picometer. So that means none of these structures of benzene can explain all the properties of benzene. Means they are not actual structure of benzene. Actual structure of benzene is this one, and that is called resonance hybrid. Resonance hybrid is always more stable than any of the resonating structures. So, if we talk in terms of energy, energy of resonance hybrid is least because it is most stable, and canonical structures, different canonical structures, obviously this is most stable resonating structure. The one which has least energy among resonating structures, that is most stable. So the difference between these two is called resonance energy. So resonance energy is equal to difference in energy between most stable resonating structure and resonance hybrid. Difference in energy between most stable resonating structure and resonance hybrid, that is called resonance energy. That means lower the energy of resonance hybrid, more is the resonance energy. So higher is resonance energy, more stable is resonance hybrid. For example, resonance energy of benzene is 150 kilojoule per mole. How to draw resonating structure, or what is the condition for a resonating structure? Favorable conditions to draw resonating structures. So to say these favorable conditions, first we draw resonating structure of carbonate. In carbonate, how many bond pairs are there? In carbonate, how many bond pairs are there? Bond pair, shared pair in carbonate. In carbonate, how many bond pairs are there? I have done it before, but number of valence electrons they have calculated to draw Lewis structure. Carbon has 4, each oxygen has 6 plus 2 for 2 negative charges, okay? So 24, and number of electrons required to complete their octet, 4 into 8 means 32. That means number of shared electrons is 32 minus 24, that is 8. So number of shared pair equal to 8 by 2. I have explained it earlier, 4. Okay, that means shared pair are 4. Say now, there are 3 oxygens. Oxygens are 3, but shared pairs are 4. So as shared pairs are 4, so 3 we can arrange like this. So 1 that may be at this position or this position, any one of them. So if we draw double bond here, so there are other 2 single bonds. So 1, 2, 3, 4, 5, 6, 7 and 8. 8 lone pair should come. Unshared pairs are 8. Okay, so this is resonating structure of carbonate. We can draw like this. If double bond is here, can be. Or so now listen, double bond may be at this position or next position or even next to it. Means these 3 are called resonating structures of carbonate. So in resonating structures, say position of atoms remains same. There is no change in position of the atoms, but there is different distribution of bond pairs and lone pairs. Distribution of bond pair and lone pair is different. Like say, if we say here there is a double bond, if this oxygen has 2 bond pairs, 2 lone pairs, but same in other structure, this has 3 lone pairs and 1 bond pair. Okay, and see this one remains same, but these 2 interchange. In this case, these 2 interchange. Got it? That means in what are the favorable conditions to draw resonating structures? First condition, position of the atoms remains same. Means different contributing structures or resonating structures. Different contributing structures should have same position of atoms. That you can see. In all of them, position of the atoms is same. There is no change in the position of atoms. But there is a change in the position of bond pairs and lone pairs. Okay? But number remains same. Bond pairs 4, 4, 4. Lone pairs 8, 8, 8. In all the resonating structures, bond pairs are 4 and lone pairs are 8. It's true for all the structures, but distribution is different. So contributing structures, the contributing structures should have same number of shared pairs and unshared pairs. they differ only in their positions. Their positions are different. Okay. Now, third point is contributing structures. Contributing structures should have nearly same energy. Should have nearly same energy. Their energy should be almost equal to each other. There is a slight difference in their energies. Because as bond pair and lone pair are same, position of the atoms are same, so they have almost similar energy. Okay. Then in all the contributing structures, in all the contributing structures, like charges should not reside on neighboring atoms. Means adjacent, there should not be positive charge or negative charge. It may be positive and negative, but two like charges, two positive charges or two negative charges should not reside on the adjacent atoms, on the neighboring atoms. So these are the conditions. So first we have drawn structure of carbonate, benzene, ozone. Carbonate is very important. Structure of carbonate, that is very important. Let us draw structure for nitric acid. Nitric acid or nitrate ion. Okay, nitric acid, HNO3. So keep in mind, in HNO3, nitrogen it is like this, because nitrogen can form maximum 4 bonds. A lone pair, it is like this, or it may be like these are the resonating structures of nitric acid, HN3. So in HN3 is HN double bond N or HN or HN triple bond N single bond N. Now basic question is, you can ask, okay, why you write double, single, triple, single? Say, so how could we calculate? See, if we have N, leave H, remove H, it is N3 negative. Okay, in N3 negative, number of valence electrons 3 into 5, 15 plus 1 is total 16. Now, to complete their octet, 3 into 8, 24. So, number of shared electrons, you can calculate 24 minus 16, 8. So, number of shared pairs equal to 4. Okay. So, shared pair of 4 between 3 nitrogen atoms, it can be double 2 2 or 1 3 or 3 1. So in this case, say total 4, so 2 pairs, total 4 plus 4, 8, done. 2. Here 3 lone pairs, 1 bond pair, 1 lone pair, 1 lone pair, 3 lone pairs. So you can say in N3 negative, this is called azide. There are 4 bond pairs, 4 lone pairs in azide. Okay. Here same. Here I attach H plus. So it is like it has 1 lone pair, it has 2 lone pair. Here it has 2 lone pairs, 1 lone pair. No lone pair. Again no lone pair and 3 lone pairs. Now another method to calculate formal charge. I think we are running short of time. Okay, see, in this case nitrogen has how many valence electrons? 5. 5. So 1 is shared 6, 7, 8. 5 valence electron it has and 3 are shared. So that means its formal charge is 0. Its formal charge is 0 because 5 it has and 3 are shared. So total 8, that means it's okay. Nothing to and no electron to gain or lose to complete its octet. This nitrogen, it has 5, 4 are shared. It has 5 valence electrons and 4 are shared. So it should have 9 electrons. That is not possible. That means it loses 1 electron. So it has plus 1 formal charge. What about this? 5 electrons, 2 are shared. So 5 plus 2, 7. That means one more electron is needed to complete its octet. Means minus 1. So this is the method to calculate formal charge. What about this? Tell me. What is the formal charge on this nitrogen? This nitrogen. This nitrogen. Fast. Do it fast. Can you calculate for this? This nitrogen has how many valence electrons? 5. Any nitrogen has 5 valence electrons, okay? Out of 5, how many are shared? 2. So 5 plus 2, 7. But it has 8. So minus 1. This nitrogen, 5 valence electrons, 4 are shared. So 9. 4 are shared. So 9. That means it loses 1 electron. So plus 1. 5 plus 3, 8. Are you getting this? 5 plus 4. 3 on one side, 1 on other side. 5 plus 4. 9. That means it has plus 1. 5 plus 4. Very good. B plus 1. Very good, Namita. Plus 1. Again plus 1. Tell me what is the charge, what is the formal charge on this nitrogen? 5 it has, 1 is shared. So 6 and 2 electrons are required, minus 2. So tell me, out of these 3 structure, which one is most unstable? Out of these 3 structure, which one is least favorable? Out of these 3 structures, which structure is least probable? Third one, because in this case like charges reside on the neighboring atoms. Like charges reside on the neighboring atoms, and because they repel each other, like charges repel each other, so this is the least stable resonating structure or least favorable resonating structure for hydrozoic acid. That's all for the day. Thank you so much.